All right, so the final speaker of this extended morning is Adámek, and he will talk about Finitary monads for pose.
Right. So I would like to join to the praise of the organizers. I'm so happy that they made this conference possible. And the topic of my talk is a simple question concerning the fact that every categorical school kid knows if you speak about monads on the category of sets, then to say that something is a finitary monad is nothing else than to say you are speaking about a variety of finitary algebras. This science can be made absolutely precise by saying, look at the category of all finitary monads and monad morphisms. It is dually equivalent to the category of all varieties and concrete functors, those commuting with the forgetful functors. And my question is, does something like that hold for posets? So as a base category. So we now talk about ordered algebras and monads possibly enriched over the Cartesian closed category, or maybe general monads on the ordinary category of posets. And I will give you several affirmative answers. Why several? Well, on the monad side, a finitary monad over set has lots of pleasant side properties. For example, if you take a variety of algebras, co-equalizers are complicated or algebraic, but reflexive co-equalizers of reflexive pairs are simply created by the forgetful functor. Therefore, every finitary monad automatically preserves reflexive co-equalizers. And so there are additional properties. On the variety side, yeah, the question is, what is a variety? So a variety is always a class of algebras for a given signature, whatever signature is, presented by equations, or in the poset case, possibly inequations. And my talk will have two parts. One is where the signature is classical. So this is nothing else than a collection of sets, indexed by natural numbers, and sigma n are the operations of arity n. And the second part is for more generalized signatures. Okay, when we are here, if you meet your friend, the universal algebraist on the street, and ask him what is a variety, I don't think he would hesitate much. He would say, well, a variety of ordered algebras, well, you start with an algebra having a underlying poset, operations are monotone. What else can it be? That you take terms and you instead of equations in the universal algebra, you will consider inequations, in the sense an algebra satisfies this, provided that for every interpretation of the variables, the corresponding homomorphism takes T and S to comparable pairs. And morphisms are, of course, monotone homomorphisms. And that's what I would simply call a variety. And now I ask, what is it that it corresponds to on the side of monads? And the answer is known since a paper by Kurz and Wellebil 4 years ago. Namely, strongly finitary varieties. Which means that your endofunctor on posets is a left-Kan extension of its restriction if you take the category of discrete finite posets as a full subcategory of pos. So then 10P is simply left-Kan extension of its restriction.
So, sorry, did you want to say strongly finitary monads?
Sorry?
Did you want to say strongly finitary monads?
I did, thank you. Now, due to the dissertation of John Burke, we know that this is nothing else than the following three very natural conditions. First of all, T is enriched, so locally monotone. Then it is finitary in the classical sense, so the ordinary endofunctor preserves filtered colimits and preserves reflexive coinserters. So just like reflexive coequalizers are set-based for classical varieties, reflexive coinserters are pos-based for varieties of ordered algebras, which explain this. Now, unfortunately, that paper was concerned with other properties, so it was a byproduct of a paper of something like 45 pages of a very technical material. And so I suggested, couldn't we present a direct proof? And we did in a joint paper just recently, accepted. Dostal, Velebil, and myself proves the same thing. So varieties, classical varieties of ordered algebras are precisely strongly finitary monads by using, well, Beck's theorem plus, so Beck's theorem is well known. What is less well known and should be generally known, wonderful observation of Max Kelly, that if you have a monad T, then algebra, so I mean Eilenberg-Moore algebras on a given object A are nothing else or correspond to monad morphisms from the monad to the continuation monad of the object A, which is the monad which gives to every poset the power of A to the monotone maps into A. So these are the ingredients of a proof, which is now a couple of pages. So there is one corollary that's actually disappointing. I didn't speak about examples yet. So let me amend this. And for example, ordered monoids would be a nice example. What is it on the side of monads? Well, the classical free monoid monad of words, but now X is a poset, so I have to tell you how this is ordered, and it's ordered minimally. Which means two words are only comparable if they have the same length and if they are comparable in X component-wise. So my next example is ordered monoids where the neutral element is the least one. So here, so in this case, in the first case, I only use equations. This is the first time I use an inequation between terms, which tells me this. And the corresponding monad is a lot of words, but this time a word V is smaller or equal to W if and only if you find a subword of W, which is comparable with V in the minimal order. Okay, so 2 examples and not very exciting ones. Where are the exciting examples? Surprising answer, there are none. Because a corollary of not of the theorem, but of the new proof that we have is that every strongly finitary monad on pos is a lifting of a finitary monad on set. So for every variety in this sense, you will find a classical variety which acts in a disappointing way, just like these 2 examples suggest. By the way, what does it mean to be a lifting? So you have now 2 endofunctors. One is of pos and the other is of set. And then you have, of course, the forgetful functor from posets to sets, and this commutes strictly. Okay, so that was the case where I said I have classical signature. The interesting examples happen, as we now know, only when the signature is generalized. And here I follow the footsteps of Kelly and Power, who in the 90s described finitary varieties on enriched, locally finitely presentable categories. And in the case of posets, what they would take as a signature is a collection again, but this time it's not indexed by finite numbers, which represent finite sets, but by representing the collection of finite posets. So P is a finite poset, and you take for every isomorphism type just one. And so now I have to say what is an algebra. I didn't have, well, I said it before, but now it's an algebra is, of course, a poset. And if you give me one of your P-array operations, then the corresponding map assigns to every interpretation of the variables, but one which is monotone, an element of A. So in a way, it's a partial operation because not all n tuples are described. And homomorphisms are monotone maps that make the obvious squares commute. Example. No, I am not ready for examples. I just told you what sigma algebras are. Now I'll take terms, sigma terms over some set of variables. And I will consider, again, inequalities, but also inequalities are parametrized in finite posets. So this inequality says, let P be a whatever finite poset of variables containing the variables of T and S, then I impose such an equation on an algebra. And what does it mean? It means that for every interpretation of the variables, but it has to be, of course, monotone, the corresponding elements that you get are again comparable. Example. take ordered monoids and impose the following commutative law only for elements that are comparable. And here you already get an interesting monad that is not a lifting of the word monad. And what is it that if I now define a generalized variety, I mean a generalized signature like this, and a couple and a set of inequations in this generalized sense. And this gives you a full subcategory of the category of all ordered sigma algebras. And what it corresponds to are precisely the finitary enriched monads. Paper that also got very recently accepted was written by Ford, Milius, Schroeder, and myself. And the technique is slightly, well, it's more complicated than what I mentioned before because of the constant trouble you have with everything being by just partial. So you define your terms just like in classical algebra. So for defining the terms, you simply completely ignore the ordering of this finite poset P, but then you have to have your interpretation of terms partial, and you need some work to do that. So I started my talk with the question, finitary monads are the same as varieties. Is there a corresponding result for posets? And to answer this, I now expect that I want to have this part for all finitary monads. The story is completely analogous. It came from the same paper. It's completely analogous, except I don't insist anymore on sigma A, the operations of my ordered algebra, to be monotone. I was quite unhappy when I first saw this result, because who cares about non-monotone operations in ordered algebras? But that's the message. The message is the good thing are the enriched monads, and the non-enriched ones are not so good. On the other hand, they are also not all that bad, because probably the most well-known example of ordered algebras are ordered groups, ordered vector spaces, and things like that, which have non-monotone operations, namely the inverse. So how am I this time?
4 or 5 minutes.
Ah, wonderful, wonderful. Because I want to come to a compromise between these two worlds. The compromise is that I now have sigma classical, so operations are again completely defined, n-ary operations as we know them, but I still impose some order on variables between inequations. And I will tell you why I am interested in this case, because that was a motivating case of the whole project. Namely, in computer science, there is a series of papers written by Mardare, Plotkin, and Panangaden, very famous computer scientists, devoted to precisely this type of varieties, but on metric spaces. And the papers are very interesting and from a category theorist point of view, very badly written. So somehow the feeling is these guys should know what they are doing. And I think that we now do. So I will not speak about metric spaces because I would have to define things for more than 4 minutes, which are now just 2. But I will tell you what these, in case of whole sets, these monads, where you have classical signature but non-classical inequations, correspond to. And these are the enriched finitary monads preserving epimorphisms. And this comes from a non-existing paper, I mean, a preprint that's under preparation of Jiří Rosický and myself. And by the way, for the metric case, we have the same result, where unfortunately, instead of saying epimorphisms, one has to say surjective morphisms, which in metric spaces are not the same. Thank you for your attention.
Thank you very much. The comments or questions? Yes.
Thank you for your talk. It has been recently, there are some progress also in the post-enriched exactness properties, like regularity and exactness in a post-enriched setting. Do you plan to characterize your varieties in that sense?
Well, for the classical case, that was exactly the goal of Kurz and Vellebil. And as I said already, it's a really tough, long paper, which simply evolved before they knew about the corresponding paper of Garner and Burke, where these things are done on a better level. This is a citation of Vellebil. I'm not criticizing, I'm citing.
Okay.
Other comments? Yes.
Yes, thank you for a very interesting talk. Another place where this could be interesting is for pro-finite algebras, right? In the Reiterman theory, in algebraic automata theory, if you want to talk about distributive lattices, so sublattices of languages rather than Boolean algebras, Jean-Éric Pain has a whole ordered monoid, which is Priestley duality essentially. And there you then get an inequation theory for the subvarieties. And so one question is whether you can make this fall into that. And second question, which is a big problem they are having, is when you have an ordered variety, finding what the Boolean consequences are of axioms. So like if you have an order variety and you have an order axiomatization, then you can look at the Boolean consequences. Like for example, if you look at the bounded quantifier height formulas, you look at the positive ones, you can understand what the inequations are quite easily. But now you want to take the Booleanization, and that would correspond to looking at the consequences that are equations, and this is generally a very hard problem.
So maybe to the last question, there is a relevant paper, which is a follower of the paper I mentioned before. I mentioned here before, by all the authors except me. So thank you, thank you. So Ford, Milius, and Schroeder have now a Calco paper just delivered yesterday, where they attend to things like that. And for the first one, Well, I don't know. It's really interesting, and thanks for the question. And I'm sure I'll give it a thought, and I'm not at all sure that there will be a result. Yeah.
Any other brief question? Very brief.
So for the classical signature, the two monoid examples that you gave, am I right in understanding that they both have the same, they're both lifts of the same free monad on sets?
Yes, they are both lifting of the same monad, namely of the free monoid monad from set. Yes.
Yes. So you gave the impression that it was boring in the sense that it sounded like there was a correspondence, but you have given two examples where you get a different ordering depending on what extra axioms you impose. So
Yes.
Is there some sense of how much complexity there is, like how much extra can be added to a given set monad when you lift it?
No idea.
Maybe I have a brief speculation or question. So you talked about the enriched environment in the Boolean 2 chain. You mentioned enrichment in the reals. Where do we go from there? Could it be that maybe we can manage enrichment in a at least thin monoidal closed category?
Well, that's a plan that Isabel is fostering, and I hope we'll be able to tell you something in some time. Yeah,
We need
that's a very
future-
good suggestion. Yeah.
Future meetings.
Yeah. Well, I didn't want to restrict that much.
Is there an online question? It's none. So let's thank the speaker again. I believe there was an announcement by Ivan on the web.
Hello, so I just wanted to say that Ithaca Fest and the activities of Ithaca will start again from September. And so we will have our fest meeting online, of course, the 28th of September. And if you check out the webpage, everything is already updated, so you can see who's gonna talk and who's gonna be with us. So come to the webpage and bye.
Thank you. Bon appetit.